the 3.3 assignments were programmed to turn on, and I don't know what I did wrong, but they never turned on. So they're now available, but you were supposed to have those for the weekend and you didn't. It's not that big a deal though, because we're going to finish our review today. And so I'll just, they're posted now, and then after today, you should be able to tackle those assignments, no problem. Remember where we were. Let's just do a quick review. So we've been talking about vertex form of a quadratic function, right? And just to put this in some context here, remember that we talked about how to do transformations of functions. The idea being that we could take any parent function, and once we know what the parent graph looks like and we know what some key points are, we're able to do a variety of transformations, right? We can do translations horizontally and vertically. We can do reflections, right? And we can do vertical dilations as well. And we may actually come back at the end of the year, and I might show you, depending how much time we have, I've got a few little topics here at the end that don't really fit in the context of what we're doing right now. But we might come back and revisit this, and I might talk to you about horizontal dilations as well. But we'll see. It's not that essential. It's kind of a higher level topic. It's not really an Algebra 2 topic, but it's something that in an honors class we might want to take a quick look at. We'll see if we get there. Okay, so we want to review this stuff just briefly, and then I want to introduce just a couple of other offshoots of this topic. One of them is nonlinear inequalities. And so we'll look at the example of quadratic inequalities. Not a big stretch at all. And you'll be able to anticipate, I'm certain, exactly what that's going to end up looking like. And then the other one is we want to maybe look at a more complicated piecewise function that's going to integrate these quadratic functions as well as maybe a linear function. Okay, so that's where we're headed with this. Let's just jump in and tackle a couple examples. And I think it's pretty likely, I know this is rare for me, but I think it's pretty likely that today, I can't promise, but I think it's pretty likely you're going to have a little time at the end when you could work and maybe, get some questions answered if you want to individually jump into a breakout room or something. I believe we might actually have a little bit extra time today for once. So we'll see. But having said that, it probably won't happen. You know me, but I'll try. Okay, so quick review. Remember, we talked about vertex form latter half of last week. So a vertex form is just a form that includes the coordinates of the vertex in the form of the equation, right? And so here we've got a quadratic equation written in vertex form. You can see that, a times the quantity x minus h squared plus k. H and k, of course, give us the coordinates of the vertex, like we talked about. Remember, we've got a parabola has reflective symmetry, right? It's got folding symmetry or reflective symmetry. So we talked about the fact that we've got this vertical axis that goes right through the vertex. And so the equation of that vertical axis is always just going to be x equals h, and that's going to split the parabola evenly right down the middle. And then we have this vertical dilation factor A. And we're going to get a little bit of practice using this stuff again today, right? So here's our first example. Now this looks a little different here, right? We're going to kind of kill two birds with one stone here, and we're going to do a little bit of review. And while we're at it, we're going to look at a nonlinear inequality. So remember, we talked last unit about graphing linear inequalities, and that was really no big deal, right? We had a boundary line, as you'll recall. The boundary line was, remind me real quick, Adelaide, when was the boundary line solid when we graphed linear inequalities? Questions for Adelaide. When we graphed inequalities, linear inequalities, when did we end up getting a solid boundary line, and when did we get a dashed boundary line? What distinguished between those two things?
Whether it was equal to.
Okay, good. So perfect. So if it includes the equals, then the boundary line is included in the solution, and so we have to have a solid boundary, right? If we didn't include the equals, then the boundary line is not actually included in the solution, and so it's dashed. Good. And then we just shaded. Remind me real quick, Abby, how did we decide how we shaded those lines? We put the inequalities into slope-intercept form. So we had y is, some symbol, either less than, greater than, mx plus b. And how did we decide which way we shaded the half plane?
If the equation was either greater than y, we would put it to the right, shade the right side.
You mean above, right? What you're saying? Shade above the line. Good. Mm-hmm. And if it was less than, we shade below, right? Which makes sense if you think about this, because when we're comparing y values, if we had something like, and let me just write this down, if we had something like, for example, if we had y is greater than or equal to, and I'll just leave it as mx plus b, right? We've got some boundary line that we know how to graph, and we want the y values that are greater than the boundary line. We know that the y-axis is our vertical axis, of course, and so we know that we want the y values that are greater than the boundary line. A greater y value means further above, right? Further up in the vertical direction. And so we shade above when we're greater than, below when we're less than. And so now we're going to look at something that's a little different. Now we're going to look at an example where we've got f of x, or just fancy name for y, right? F of x is less than something that's nonlinear. Okay, what do you think? How do you anticipate we're going to deal with this? And we'll work through it here. But Mr. Demanu, what do you think? What do you anticipate we're going to get from this? What might the steps that we're going to take be to tackle this problem?
Probably find out the vertex point by doing the H and the K.
Okay. Okay.
And then from there you would look at the negative 2/3, and then that would mean that it's going to be going downwards.
Correct. It's going to open down. Good.
And so then you would just go over 3 and down 2 or something like that.
Okay, well, so we're gonna have to deal with that, right? We're gonna have to deal with that vertical dilation. We'll practice that today. I've got a little tool built today that'll help us with that, because that's one of the things we want to finish with. But so let's compress all those things you said, and let's just summarize that by saying we're going to graph the parabola, right? We're going to have this parabola that we're going to graph, that's going to look like negative 2/3 times the quantity x minus 3 squared plus 1. What about the fact that we're not including an equal sign there? What do you think that's going to do for us? Chloe? When we graph that parabola, how are we going to graph that parabola if we're not including an equal sign with this inequality? Okay, good. So the parabola is going to be dashed, just like we had a dashed boundary line in our previous examples last unit. Okay, and then the very last part of this, Dalub, what do you think about the fact that we're graphing the y values that are less than our parabola? How do you think we're going to end up shading here? Yeah. So we're going to shade, it's going to be a very weird looking region, but we're going to shade that region that sits below our, really ends up being a parabolic boundary. Instead of being a linear boundary, we get this parabolic boundary. Does that make sense? I mean, really, this just follows from the same kinds of stuff we were doing last unit, only instead of getting a boundary line, we're getting this parabolic envelope. That's not really, it's just going to look different. It's going to look funny. But let's focus on the first things first. Let's deal with this parabola first of all. Okay, so Mr. Saxton, can you tell me what the coordinates of my vertex are?
They're going to be 3, 1.
3, 1, correct. Good, 3, 1. Because remember, h is the value that's being subtracted from x, and then k is the constant, right? We compare that to our vertex form. right? So we're just really asking what values, what numbers would we have to plug in for H and K to get that result? Well, we plug in 3 for H and 1 for K. Okay, good. So we know then that the vertex is going to be at 3, 1. So it's going to sit right there, isn't it? Here's where this thing gets a little bit trickier. The dilation factor is negative 2/3. So it's been a whole weekend here, and this is kind of a weighty topic. So let's just take a second and let's just kind of talk about what this all means. The negative 2/3, that vertical dilation factor, what does that mean? What does that mean? Somebody want, and I'll throw this one out to the group. Anybody want to just pitch in? Just a free for all here. What do you think? Anybody want to pitch in on that one? Who feels like they've got something to contribute? I want to know, what do I do? I know where the vertex is. What do I do with that vertical dilation factor of negative 2/3? Okay, when you say the y value, you're talking about the y values on what? Okay, and go ahead. Keep going. I'm sorry, Maria, I cut you off. You keep talking.
So you multiply the y values by negative 2/3 of the points on the parent function.
Good, on the parent function, right? On our parent function, which would just be the simplest parabola we could build, which would just be y equals what, Carrie? What's our parent function here? What's our simplest parabola, our parent graph that we tweak to get more complicated ones? Yeah, just x squared. Yeah, good. Okay, so we're going to, so once again, let me summarize what Maria just said. That was a good answer. We're going to multiply the normal parent heights of the function. When we say heights, we're talking about the vertical distance from the vertex, right? We're going to multiply those normal parent heights by our vertical dilation factor to get our tweaked or dilated heights. So I've got this, I think, and I'll make a link to this too. So you guys, and I'll put this on Google Classroom, so you can just, if you want to go back and just mess around with this yourself, you can just play with this as well. But I built a little Desmos graphing document here that should illustrate this a little bit. So would everybody agree this is our parent graph, right? This is a y equals x squared. We know that we start at the origin, and then I go whatever amount my input is, my x value. So as far as I go to the right from my origin, I'm going to go up that amount squared. So I go over 1, I go up x squared, over 2, up 2 squared, over 3, up 3 squared, etc., right? We're going to multiply those parent heights by negative 2/3, right? We want to know which one of those would be most convenient to multiply by, though, right? So if I scoot over to the right, well, there's a height of 1, there's a height of 4, there's a height of 9 when x equals 3, and there's a height of 16. Which one of those heights would be most convenient to multiply by negative 2/3? What do you think, Kendall? Questions for Kendall. Which one of those heights, 1, 4, 9, or 16, would be most convenient to multiply by negative 2/3?
1.
I could multiply 1. Let's see what happens. So if I make a negative 2/3, I'll tell you what, I'm going to make it 2/3 first. What does the negative do? Liliana, what does the negative do if I have a negative vertical dilation factor? What's the only thing the negative does? Yeah, it just reflects it, doesn't it? So to make things a little bit easier, let's just focus on the 2/3 part first, on the fraction part. So there's my dilation factor. Look what that does. It's going to pull the red parent graph. It's going to squash it down a little bit, isn't it? Well, look what happens here. If I go to x equals 1, my new height, my original height was 1. I'm going to multiply that by 2/3, and I'm going to get 2/3, 0.667 if I round it to 3 places. That's not very convenient to graph. Which one might be better, Kendall? You got a different idea?
The 3, 9.
How about 9? Yeah, good, because 9 is divisible by 3, right? So if I multiply 9 by 2/3, the 9 and the 3 are going to reduce. That's a good idea. So if I go up to 3, look what happens, right? When x is 3, my parent height is 9, and that's what I'm multiplying by 2/3 to get 6. There you go. That's much better. And then if I want to make that a negative 2/3, all that's doing now is I'm multiplying my original parent height of positive 9 by negative 2/3, which means I get a height of negative 6, right? So this is what the shape, if I look at this part right here, this is what the shape of my parabola, how it's going to be transformed when I multiply by my vertical dilation factor of negative 2/3. Now, all we have to do is apply the thinking we just did here in dilating this parent graph. We're just going to apply that to our graph, right? Well, here's our vertex. We said that normally if we went over to the right, oops, there we go. If I went over to the right by 3 from my vertex, I would normally go up 9. So 3, 6, 9. Right? So there's a distance of 9, and I normally would have a point right there. And so my parent graph would just look kind of like that, right? But we're multiplying by our vertical dilation factor of negative 2/3, right? A is negative 2/3. So 9 times negative 2/3, we calculated to be negative 6. So instead of going up by 9, we're going to go up by 9 times negative 2/3. So we're going up by negative 6, which is the same thing as going down 6. And so there's another convenient point for us that falls in a convenient place for us to use to sketch. And I should mention that, are we graphing or are we sketching? We're sketching. Right? A graph is a perfect representation. Anytime we do something by hand here, it's really a sketch, isn't it? Now, if we want to graph something in this day and age in math, we use a graphing utility. When we're doing something on paper, we're sketching it, right? So where could I put another point? Where could I use my symmetry here to create a third point to kind of seal the deal here and give us a better chance to more accurately sketch this thing? What do you think? Olivia? If I wanted to add a third point down there that would help me sketch this thing a little better, how could I take advantage of the symmetry of a parabola?
So you would just reflect it across the line of symmetry.
Perfect. So we'll just reflect it over this line of symmetry. Good. So here's our line of symmetry, and that's just what x equals 3. And if we reflect this guy over the line of symmetry, doesn't it just end up right there? I didn't draw that line very well. It's supposed to go through there, isn't it? And so there's another point. And now you'll see my artistic limitations here in action. But there's our parabola. Okay? So now we're going to have to go back. We did that in the context of just graphing a parabola. Now, once we were sure we're okay with that, we'll go back and look at it in the context of the larger problem here. Give me a 1 to 5 on that part, though. Either flash me fingers or just type it in chat. How are we doing on that? Okay. Make sure I'm getting feedback from everybody, too. It really helps me to know where we are on this. I don't care if you want to just quickly flash fingers, that's fine. Either one, though, when I'm asking that, let's make that quick, and it's just a good way for me to get a kind of take the temperature of the room here a little bit. So we end up then with this red parabola. Now let's go back to the context of the bigger problem. We're graphing this inequality. So I graphed that as a solid boundary. You already told me that that's really not a solid boundary. It needs to be a dashed boundary. This is getting kind of messy. I'm going to go ahead and grab everything here and go to another page so we can focus on the graph of the inequality. This is getting a little too messy for my liking. Okay. All right, so you already told me that we had a vertex at 3,1. Whoops. So we were over 3, up 1, and we said that we went over by 3 and up by 9 times negative 2/3, which meant down 6. So we got a point there. Whoops. We got a point there. Oh, third time's the charm. Got a point there, and we got a point there. And I'm going to connect these now with a dashed boundary. Those aren't very good dashes. That's a little better. So there's my parabola, extends forever. And if I'm going to graph the region where f of x is less than my parabola, less than the boundary, it's not a boundary line. In math, we call this an envelope. It's just a shape that's serving as a boundary. You told me to shade below. So as bizarre as this looks, this is what our graph ends up looking like. That's it. Okay. Let's graph that just so we can see a better picture. Let's graph that on Desmos. How about? Okay, so if I graph f of x is less than 2/3. Oh, it won't. That's bizarre. Huh.
I think it only looks like it's one.
Yeah, I think it does. I think you're right. So when you're doing inequalities that are nonlinear, you have to use y instead of f of x. Okay? Well, live and learn. I guess, maybe I'd seen that before, but I'd forgotten that. Okay, and then we can go in here, and I'm just going to highlight the vertex too while we're at it. Okay, give me a 1 to 5 on that. Does that make sense? Okay, all right. That's good. We're getting there. Let me take a picture of this for our notes. So you could get something then. Is that going to fit? I'll go to the next page. So what if I change this, for example, to be greater than or equal to? Oops. Greater than or equal to. Now it gives me everything shaded above that, so it's kind of a equally bizarre looking shape, right? If I wanted to do a system of nonlinear inequalities, I could get something pretty bizarre then, couldn't I? What if I added another parabolic inequality to this? What if I had something like y is greater than or equal to, how about x squared minus 4. Oops. Man, I'm kind of... There we go. Squared minus 4. And let's change the colors. Make that blue. And now that's kind of a weird looking region, but then that would be the solution of that system of nonlinear inequalities, right? Everybody see that? Okay. Yeah, I'm going to take a picture of that too, just to put in our notes, just to remind you. Okay. There we go. All right, next issue. What about something like that? Everybody stare at that for a second. Okay, it's a piecewise function, right? We dealt with piecewise functions way back at the start of Unit 3, but our piecewise functions were always, the pieces were always linear. So what happens here if we get a piece that's nonlinear, right? A piece that's quadratic. And really, this is just kind of a disguised way for me to get a little practice with the quadratics, but it's a different context, and it's something worth maybe taking a quick look at. So what do you think? How are we going to approach this one? Suggestions. Sarah, how do you think what might I do here to tackle this piecewise function? Whoops, I think Sarah, she she hung up and she meant to hit the microphone and she hung up. I've done that before. Did you accidentally hang up, Sarah? Yeah. That's all right. I've done that many times. What do you think?
Well, the first one, then you could just graph it like a normal one, but you would only fill in the points that were less than -2.
Okay, good. And then the second one, we're only filling in the points that are greater than -2. Okay, remember when we did this, and this is good for us to review a little bit. Remember when we did this, one thing that was convenient was, could we divide up the XY plane into some regions for doing this graph? Well, where might I want to kind of subdivide this thing? Where do I want to put a boundary? What do you think? Sarah, you have a suggestion how I could maybe make a boundary here that would be helpful in graphing this?
Yeah, you could just put a boundary at the line x equals -2.
Okay, good. How about the line x equals -2? Okay, so let me add that. I'm going to get to play with my toys a little bit here. This is always fun. Okay, so x equals -2 is right there. Oops. Oh, darn it. So there's our boundary. Everything to the left of that is going to be this boundary line. So let's color code this. We'll do this in blue. We want to graph that line to the left of our boundary. That's not a very dark boundary, but oh well, we can see it, I guess. I think I can make that. I think I can fix that. How about if I go... There we go. I'll do that. There we go. A little darker. Okay, so now what can I do about that? I want to graph that blue line in the blue region, which is over here. So in the blue region, we're graphing the line y equals -x minus 6. I'll remind you about a couple things. Remember that we there's different ways we can approach this. And one way we could approach this would be if we were just going to graph this line very lightly and then darkly fill in the part of the line that is in the half plane defined by this boundary, right? The half plane defined by the boundary line x equals -2. So only the stuff over here, right? And that's typically a lot of times how this is taught. But remember, we had kind of a different idea here. We could use a t-table also, couldn't we? Right? We could use a t-table and we could just pick a couple points, convenient points that are in that blue region, right? So if we make a t-table from this, and here's our t-table. Let's see. We're going to be way down here, aren't we? So I'll make my t-table up here. So let's pick some x and y values that would be convenient for us. What are some values over here, some values of the input x that would be convenient given the fact that we have a fractional slope there? What do you think, Jace? What's a good input value for me for x? I got to come up with, really all I need are 2 points, right? I'm graphing a line here. If I have 2 points, I can just connect and extend.
You could do, so it has to be less than -2, right?
Right, and we could do -2. That would be fine too. That actually might be a good one because that's on the boundary.
So if we did 4 for x, right?
If we did 4 for x, but that's going to be over.
Or, yeah, -2 because you would, oh yeah. So if we do -2 for x.
Okay, -2 is a good value. Good. Okay, let's plug that in and see what we get. So you got, if I plug -2 in, -1/2 times -2 is 1. You're right. -6 is -5. So there's 1 point. Now, when I plot this point, being as we're not including -2 in our region, how do I want to plot that point on my graph? Jace? Do I want it to be a solid or open point?
A solid or open point?
Yeah, because we're not including -2, right? -2 is just our boundary of this line. It's an endpoint, but we're not including it, right?
Okay. So I have no idea. Solid?
Okay, well we'll come back to that part.
I have no.
Okay, that's okay. We'll come back to that concept. I'm probably throwing too many things on you at once. So there's 1 point we're going to use. What's another point we could use in our region? We got to be less than -2. I want to make another ordered pair, so I get 2 ordered pairs. So I can connect and extend to make my line. Get an idea, Jace, for another one for me? So -2 was a good value to plug in for x. What's another value for x that would be probably a wise choice to plug in for x? We don't get any fractions.
You could do -4.
There you go. How about -4? Good. And if I plug -4 in, I'm going to get +2 minus 6 is -4. So we got these 2 points then. We're -2. Let's plot these. -2, -5. So there's going to be a point right there. And I've got -4, -4. So that's a point right there. Okay. And when I graph this thing, that gives me the shape of my line, but I can only graph it up to my boundary. Now, Alan, what do I have to do at this endpoint of this piece of my function if I'm not including -2? That's an x value that's a boundary, but it's not being included. Questions to Alan? Oh, that's right. That I should have known that. That's right. Yeah. Let's see. Rebecca Edmonds. what do I have to do at this? I'm graphing these two pieces. I've got a blue piece, and we'll make, this is going to be our red piece, let's say. We haven't gotten to that yet, but on my blue piece, what do I have to do when I get to x equals -2 if I'm not including -2? What kind of endpoint do I need there, Rebecca?
Open.
Yeah, good. It's got to be an open, oops, wrong color. It's got to be an open endpoint, doesn't it? Okay, it's got to be open. Jace, does that make sense what I was talking about there? I think I was asking you too many things at once, but does that make sense why I was asking about an open? Okay, good.
My brain literally like purged everything about this, so I have like I have no clue what you're talking about.
That's why I throw in some review. Everybody, that's a natural thing. That's right. We got to hit things more than once. Okay, so now what about the red part? That's a little more complicated, right? That's parabolic. So let's focus on that red part there. Let's see, Natalie, can you tell me what the vertex is of this parabola we're going to get from when we graph this thing? Where's the vertex of our parabola? Oops. Where's our vertex on this one? Questions for Natalie. Oh, okay. Okay. That's all right. We'll get back to you on something else. Liliana. 1, -5. Good. Okay, so we've got a vertex, and that's in the red region, isn't it? We've got this. Let me kind of, maybe this might help a little bit if I do. So here's our blue region, right? And here's our red region over here. This is where we're graphing the parabola y equals the quantity x minus 1 squared, minus 5. So over 1, down 5. So there's our vertex. Now we got to get the shape of this thing. So Dawson, what's our value of A for our parabola here? It's 1, exactly. Good, because we got a coefficient of 1 out front, don't we? So A is 1. So this is just a normal looking parabola. When A is 1, we're not dilating at all, right? We're multiplying the normal parent heights by 1, not changing them. So give me a couple of convenient points, Dawson, where I could use to sketch my parabola here. Well, okay, but I'm saying like if this is my vertex right here, right? So from the vertex, I wasn't very clear on that question. From my vertex, if A is equal to 1, it's an undilated parabola. For example, from the vertex, if I go 1 to the right, what should my height be of my parabola? 1, exactly. Okay. And if I go 2 to the right, it should be, no, hang on. If I go 2 to the right of my y equals x squared, the height would be 2 squared, right? It'd be 4. That's how we get that parabolic shape. We go over 1, up 2, over 2, up 4. Remember, that was that stuff, right? I don't think I took a picture. Oh, here's a good picture, right? Here's my parent graph. Normally, I went over 3 and up 3 squared, which was 9. But in this case, we had to multiply the normal parent heights by -2/3, which caused them to be dilated. Now, in our case here, we don't have to worry about that. For this current problem, A is 1, so we're not dilating it at all. I'd go over 2 and up 4, over 3 and up 9, and so on. We want to know what happens at our boundary, right? We know we're going to go back 1 and up 1. How far is it over to our boundary? Well, our boundary line is right here at x equals -2, so that would be moving 3 to the left. If I go 3 to the right or 3 to the left, Pagan, what would my height be? Questions for Pagan?
Sorry, it wasn't letting me unmute. I'm not sure.
So if I'm going on my parent graph, and remember my parent graph is always just plain old y equals x squared, right? If I go 1 to the right, I'm going up 1 squared. 2 to the right, I'm going up 2 squared, which is 4. If I go 3 to the right or 3 to the left, how far up would I be going?
3
Squared.
4.
3 squared, right?
Oh, 9.
9. There you go. Good. Okay, so I'd be going up 9, so I could go back 3 and up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's where I would end up. I'm going to make that, however, an open endpoint because look, we're not actually including, our boundary line is at -2. We're not actually including that in our red region, right? Look, that -2 gets claimed by nobody. For our function up here, x never has a value of -2 because both of these two inequalities exclude -2. So I get 2 open endpoints. And so this is what my shape ends up looking like then, right? It ends up looking something like, kind of like that. And so the blue and the red combined, that's our graph. Now, could we use a t-table over here like we did with the blue? Sure you could. We could make a t-table over here for our red parabola. That would work fine. If we do that, we do want to make sure we know where the vertex is though, right? So we know that if I plug in like -1 into my function, I know I'm getting back, or sorry, +1, not -1, right? H is +1, I should get back -5, right? Because those are the points that we identified already as our vertex, right? We already found that our vertex was 1, -5. It works in a t-table just as well, doesn't it? It has to. Math gods make sure it always works. So if I plug 1 in for x, I get 1 minus 1, which is 0 squared minus 5. Well, sure enough, I get 1, -5. I want to be able to plug in -2 to see where this parabola ends at the boundary. So if I plug -2 in, what happens? -2 minus 1 is -3. -3 squared is 9. 9 minus 5 is 4. So I know that I'm going to put this endpoint at -2, 4. Well, there it is, right? And we know we just need to make it an open endpoint. And then I could maybe do one on this side also. If I went, for example, over 2, well, 2 minus 1 is 1. 1 squared is 1. 1 minus 5. Oops, what did I do here? 2. Oh, that's right. Yeah, that's right. 2 minus 1 is 1. 1 squared is 1. 1 minus 5 is -4. So that's correct, right? We go over 2 and we go down 4. That works. Or if we wanted to go like over 2 in this direction, or 3, if I went over 3 to the right, I'd be plugging in a y or an x value of 1 plus 3 is 4. 4 minus 1 is 3. 3 squared is 9. 9 minus 5 is 4. And sure enough, if I go over 4, I go up to 4. And there's my point with coordinates 4, 4, right? So I just wanted to illustrate there that, yeah, we could use a t-table there. It's convenient, right? But we just want to make sure that in our t-table, we're identifying where the vertex is. Okay. So this is, honestly, this is pretty advanced. I mean, this is not something that shows up in any of our, the normal curriculum. But for you guys, I just want you to see, this in a slightly different context. So just understand where I'm coming from on this. I wanted you to get a little practice building another parabola, but I want you to see it in the context of just a little more complicated piecewise function. Because when this group moves forward, this is something that, for example, in a couple of years in calculus, we're going to deal with with some things like this, some more complicated piecewise functions. And so this is sort of setting you up to deal with this type of an animal when we get there. Okay. Let's see, what else have I got here? So let's maybe look at just one more quick one of these, and then how are we doing for time? 5 minutes. You know what? We're not going to get through that one. We wouldn't have time to get through this one anyway. So I'll tell you what, I'm going to give you a chance here to work on this stuff, get any questions answered, pull up those assignments, take a look at them real quick, make sure that stuff is making sense. I'll just be here to answer questions if you've got them. And if you want to jump into a breakout room real quick, I'm available to do that as well. Okay. How are we? Give me before you leave though, and jump into your homeworks here. Don't leave. You can't hang up. You got to work in class here. But before you jump into your homeworks, give me a quick little bit of feedback. How are we feeling about this quadratic stuff? Do you feel like you're able, if I give you a quadratic function in vertex form, could you graph it? Okay. And I think on the homework, I'm even going to have you maybe do the opposite, where if I gave you a graph, you're going to have to write down the equation of the function. Okay. All right. Jump into it. Bring questions next time, and we'll, bring your questions to class. I'll do a little review I'll look at the homework and see if there's anything we're having trouble with, but that ought to get you started at least. Okay. Dive in.